All right, today's lesson is going to focus on what we call a piecewise function. And just like it says, it's going to be a function that when we graph it, there's going to be pieces to that function as we graph it. Now, in this section, we'll focus specifically on pieces that are linear. You already know a very common piecewise function, and that being the absolute value of x. If you look at the absolute value of x, you have that V shape again. One of your pieces is the blue part that goes to the left. The other piece is going to be the red part that takes off to the right. But when we combine them together, we have our absolute value function. So it takes its pieces together for us to form the whole. Now in the book, there's a really good example that talks about, if you took a trip to school and back, and if you look at the time and the distance you are from home. So at time 0, you're at home yet here, and what you do is you're going to drive for a while, and you're going to get farther from home. Okay? And let's just say it's a constant speed. That would be what causes our function to be linear. Then you come upon a stoplight, and at that point, you're not moving. So that distance is staying the same. Okay? Once the stoplight is turned green again, now I'm able to drive again for a while. Let's say again it's at some constant speed. And as we do that, we finally arrive at school. And we're stopped there for a while again. Well, once we've stopped at school for a while, now what we want to do is come back home, and maybe we don't have to stop at all. And so what we have here then is a situation where we have a function. The function is, our distance from home in terms of our time. Every piece is linear, okay? But in this case we have 5 distinct pieces. Now you're going to see some functions that look like this. You're going to have a function in x, or f of x, that's going to be equal to 1 if my value that I input into that function is less than or equal to -2. Okay, so one of the things I look at is I talk about that kind of as a boundary. So I have a boundary here at -2. Something's going to happen there. Okay. The second part of my function is that f of x is going to equal 2 plus x when my value for x, my input, is somewhere between -2 and less than or equal to 3. So what that does, it creates yet another boundary. And then finally, our third piece is f of x is going to be defined as 2x whenever my x values are greater than 3. There's a number of different ways you can approach graphing this situation, but what you should notice is that I have 1, 2, 3 regions. Each of those regions will be a piece of my function. Okay. Now, what I've done a lot of times is told people to graph the functions individually and erase what they don't need. So if I start out with that first function in the yellow, what I'm actually graphing is f of x is equal to 1. Okay. Or again, remember that's the same thing as y equal 1. And hopefully remember that when we have y equals 1, okay, my slope is 0, so I have a horizontal line. So here is the graph of y equals 1. Now, the piece you need to recognize, though, is that I only want to deal with that function when my x value is less than or equal to -2. Okay. This red boundary here is when x is equal to -2. So because of the equal sign, we want this to be part of my solution. So we're going to put a solid point there to include that. But then what I'm going to do is I'm going to erase anything to the right side because I only want, again, the x values, my input values, to be less than -2. When I look at my second function here, f of x equals 2 plus x, which I'm going to rewrite as x plus 2. Okay, so that we now have it in slope-intercept form. I have an intercept at 2, and I have a slope at 1. So I'm going to go up 1 over 1. So again, what I can do is I can sketch that whole graph and go from there. Now, remember the idea of the vertical line test. Okay. I cannot have a function if I intersect my graph more than once. And at this point right here, I'm intersecting that part of the graph and that part of the graph. So we need to get rid of part of it. Okay. So again, I'm going to go in and erase. I've already filled up this region, so I don't even need that part. Okay. But this function, 2 plus x, begins at that boundary, but it cannot have an output at that boundary. So therefore, what I'm going to do is I'm going to put an open circle. On the other end, at x equals 3, I do want to use that as an input. So I do get this output value. So again, I'm going to have a closed circle, but I don't want that in this region. And then finally, my third piece here, y equals, or f of x equals 2x. And again, y-intercept is 0, slope of 2, so I'm going to go up 2 over 1, up 2 over 1, up 2 over 1. Okay. And I'm going to go up 2 over 1 again, because I'm going to kind of look at this and say, hey, I know I don't want this chunk in the middle here. So I'm going to try and erase some of those. But I want it to start here, so I would have an open circle at that point, but it's already included as one of our, or as part of our solution, as part of my output, so we're okay with that. Now, the one thing we should always check is we should double check with this vertical line test. So as I go from left to right, do I have any place where I have more than one output? Okay, and as you can see there, because the close and the open were good, okay, those two share that same output, but it's an output for the green, not for the blue, and then we're good. The other type of function we're going to see today in terms of piecewise is what's called your greatest integer function. Okay, and it looks like this double brackets around my x. And what it talks about is I want the greatest integer, but it's not going to be bigger than x. Okay, so when I think about it, what I look at in terms of my integers, I look at the value I'm given for x, and I look at the integers on either side of it. Well, there aren't any on either side of 0. So I want the biggest integer, but it can't be bigger than 0. Okay. If I go down to 1, I want the biggest integer not bigger than 1. The biggest integer not bigger than 3. Okay. But now when I look at 0.5, if I look on both sides of it, okay, the integers on either side of 0.5 are 0 and 1. I want the biggest one, but it can't be larger than the number itself, larger than the 0.5. Well, that takes 1 out of business. It means that 0 is going to be my output. 0.75, I want the biggest integer. So again, either side 0, 1, but it can't be bigger than 0.75. 1.2, I want the biggest integer, but it can't be bigger than 1.2. So again, either side it's 1 or 2. Well, it can't be bigger than 1.2, so that's where we get 1. All right, so if I go in and start plotting some of these points, okay, I get 0, 0. I get 1/2, 0. I get 0.75, 0. I get 1, 1. I get 1.21. Then I get 3, 3. What's going to happen, if you notice here, I'm starting at the origin, and I keep moving along this x-axis, but then all of a sudden when I get to x equals 1, I jump. And so kind of like with that piecewise idea earlier, it means I get to 1, and I have to make that jump up. So what I do is end it with a open circle. So now I'm at 1, 1.1, 1.2, and again moving my way along. And once I get to 2, I'm going to make that jump. And same thing's going to happen to 2. Once I get to 3, it makes that jump. This pattern keeps going up to the right, and we can work our way backwards as well. The negatives can kind of be a little difficult to see. If I go -1, obviously, again, the biggest integer not bigger than -1 is there, -1. But if I go -1.2, okay, the integers on either side are -1 and -2, but -1 is bigger. And so that's why at that point, -1.2, I'm down here at -2. Another name for this is it's called a step function. And I think you can see why they would call it a step function. What you're doing is you're creating a set of stairs. Now, we can also deal with our transformations with the step function. And generally how I've dealt with that is to do it the easy way, is to just use integer values and create a couple of stairs and keep going from there. If you remember back from our transformation idea, again, inside we do the opposite. So I'm going to go left 2, or I'm going to subtract 2 from my x values again. So I'm going to go in here and subtract 2 from 0, subtract 2 from 1, subtract 2 from 2. This 3 again is on the outside. It's going to change my y. What it's going to do again is that's going to give me a vertical stretch. And so what we did was we multiplied every one of my y values by 3. And so what I'm going to look at then is I'm going to go to -2, 0. I'm going to plot that point. I'm going to go -1, 3. And then I'm going to go 0, 6. And I know we're supposed to end up with stairs, so I'm going to keep working my way horizontally from a point until I get right below the next one. And that's an open circle. And now look at my pattern. It's going up 3 and then moving over one spot. So I'm going to go down 3 and just work my way backwards with that one. And that's how I do a transformation of the greatest integer function.